Hey everyone, let's decode something absolutely incredible today. We're going on this really fascinating journey in this explainer, zooming all the way from the microscopic, super intricate biology of the human eye right out to the macro physics of the sky above us. So let's just dive right into it and figure out the amazing science of how we actually see the world.
Have you ever actually wondered why our sky is this brilliant bright blue, but outer space, literally just a few miles higher up, is completely pitch black? Well, by the end of this explainer, we aren't just going to figure out the answer to that mind-bending question. We're actually going to understand the underlying physics well enough to totally master these concepts for the Class 10 Science Board exams. We're bridging that gap between everyday wonders and total exam mastery. All right, so here is our quick roadmap for today. Number 1, anatomy of the eye. 2, fixing vision defects. 3, prisms and dispersion. 4, atmospheric optical phenomena. And finally, number 5, acing the board exam. Okay, let's kick things off with section 1, anatomy of the eye, the biological camera inside your head. I want you to think of the human eye not just as, a body part, but as this highly advanced natural optical instrument. It's basically a biological camera. Let's actually trace the journey of a single photon of light. First up, light hits the cornea. That's the transparent outer bulge that does most of the initial focusing, and it also protects against dust. Then it passes right through the pupil, which is essentially an adjustable hole. Its size is controlled by the muscular iris to make sure just the right amount of light gets in. Next, the light hits the crystalline lens. This is a flexible, convex structure that really fine-tunes the focus. This lens projects a real, inverted, meaning upside-down image onto the retina at the very back of your eye. The retina is like a biological screen packed with light-sensitive rod and cone cells. And finally, the optic nerve takes all those electrical signals and fires them straight into your brain, which flips the image upright and tells you exactly what you're seeing. It is wild when you really think about it.
Now, what's really amazing here is one of the eye's most incredible features, and that is the power of accommodation. You see, unlike a camera, our biological lens isn't made of hard, rigid glass. It's flexible. When you look at something close up, these special muscles called ciliary muscles contract. This actually makes the lens thicker, which decreases its focal length. But when you gaze at a distant mountain, those same ciliary muscles just relax. That thins the lens out and increases the focal length. The absolutely crucial point here is that this mechanism ensures a sharp, clear image on the retina no matter where the object is. Just keep in mind there is a limit. For a normal eye, the absolute closest you can clearly focus, your so-called near point, is exactly 25 centimeters away.
Moving on to section 2, fixing vision defects when our biological lenses need help. So what happens when the eye's shape changes, or this incredible focal length adjustment we just talked about sort of falters? Let's compare the two most heavily tested vision defects for your exams. First up is myopia, or nearsightedness. This is where you can see near objects totally fine, but distant objects super blurry. Why does this happen? Well, it's because the eyeball is too elongated, or the lens is just too curved, which causes the image to focus in front of the retina instead of directly on it. We fix this by placing a concave lens in front of the eye to diverge the light rays just a tiny bit before they enter. On the flip side of things, we have hypermetropia, also known as farsightedness. Here, the eyeball is actually too short, so the light tries to focus behind the retina, which makes near objects look blurry. To fix this one, we use a convex lens to converge the rays earlier. Now, if you ever get confused on the exam, just use this memory trick. My cat has pretty eyes. My cat simply stands for myopia needs a concave lens. Honestly, it works every single time. Aside from those two major ones, there are a couple of age-related defects you definitely need to know about. Presbyopia happens as we age. The ciliary muscles simply weaken over time, and the lens loses its flexibility, which makes it really hard to read things up close. The fix here is often bifocal lenses. Then there's cataracts. This is where the crystalline lens actually becomes cloudy or completely opaque, causing partial or even complete vision loss. Now this one can't be fixed with a quick pair of glasses. It actually requires surgery to replace that clouded lens entirely. All right, section 3, prisms and dispersion, bending and splitting white light. Let's shift gears a bit. How do our eyes actually perceive all the incredibly diverse, vibrant colors of the natural world? Well, it all starts with the vibgyor spectrum. Violet, indigo, blue, green, yellow, orange, and red. When white sunlight enters a glass prism, something practically magical happens. It's called dispersion. The white light completely splits into its component colors. Why? Because different colors of light actually have different wavelengths.
That means they travel at slightly different speeds through the glass and bend at different angles. Violet has the shortest wavelength, so it gets slowed down and bends or deviates the absolute most. Red, on the other hand, has the longest wavelength, so it bends the least. And believe it or not, this exact mechanism is the secret behind rainbows. A rainbow is really just a massive natural prism effect. After a rain shower, millions of tiny suspended water droplets act exactly like miniature prisms in the sky. Sunlight enters the droplet, refracts, and disperses into the full spectrum. Then it reflects off the inside back wall of the water droplet, which we call internal reflection, and then it refracts one more time as it exits. The catch? You can actually see this spectacular arc if your back is facing the sun.
Let's look up a little higher now with Section 4. Atmospheric optical phenomena, the macro illusions of the sky.
Now, let's see how all this builds into macro phenomena, because the Earth's atmosphere is constantly playing optical tricks on our vision. Here is a classic, highly tested exam question for you. If stars twinkle, why don't planets twinkle? Seriously, take a second to think about that. Well, the answer lies in distance and size. Stars are incredibly far away, so to our eyes, they act as tiny point sources of light. Planets, however, are much closer to Earth. Because they're closer, they act as extended sources, which is basically like a collection of millions of tiny point sources. So while the light from individual points on the planet might flicker a bit, the total amount of light entering your eye from the entire planet averages out to a nice constant glow.
So the crucial point here is understanding what causes that flickering in the first place, right? And the culprit is atmospheric refraction. See, the Earth's atmosphere isn't just one uniform blanket. It has layers of hot and cold air with varying optical densities. As starlight travels down through these constantly shifting layers, it continuously bends and refracts. So the star's apparent position slightly shifts around, and the amount of light reaching your eye fluctuates. Boom, that creates the twinkle. And get this exact same refraction is also why we can see the sun 2 full minutes before it actually rises above the horizon and 2 minutes after it physically sets. The atmosphere literally bends the sunlight right over the curve of the Earth. How cool is that?
Okay, now we come to scattering. This occurs when light strikes tiny particles like dust or gas molecules and just bounces off in different directions, a phenomenon known as the Tyndall effect. This explains so much of the world around us. For instance, the sky is blue because the atmosphere's molecules scatter the much shorter blue wavelengths way more effectively than the other colors. At sunset, that light has to travel through a much thicker slice of the atmosphere just to reach your eyes. By the time it actually gets to you, all that blue light has already been scattered away, leaving only the long red and orange wavelengths. And this finally answers our big question from the very beginning of the explainer. Outer space is completely pitch black because there is absolutely no atmosphere, no gas, and no dust to scatter the sunlight. Without any scattering, the sky is just an empty, dark void.
This scattering effect actually has a really crucial practical application too. Ever wonder why danger signals, stop signs, and traffic lights are red instead of, say, blue or green? Well, remember our spectrum? Red light has the longest wavelength in the visible spectrum. Because it's so long, it is the absolute least scattered by tiny particles like fog, smoke, or dust in the air. That means a red light can pierce right through poor weather conditions and be seen clearly from a much, much greater distance than any other color.
All right, moving into our final stretch. Section 5, Acing the Board Exam, securing full marks in CBSE Science. Okay, we've covered the biology, we've covered the physics. Now let's figure out how to avoid those easily preventable mistakes on test day. The golden rule here? CBSE board exams reward precision, not length. This is a massive trap that so many students fall into. They think writing a huge paragraph somehow shows how much they know. Look, if a question asks you to simply define power, and you write an entire story about electricity and energy, you are just wasting time and risking your marks. The examiner literally just wants to see, power is the rate of doing work. That's it. Read the command word, write exactly what is required, and make sure you use the specific scientific terminology from your textbook.
Here is a rapid-fire list of the most frequent errors that unnecessarily cost students marks. First, mixing up vision defects and their corrective lenses. Remember our trick, my cat has pretty eyes for myopia and concave. Second, confusing scattering with dispersion. Just remember, dispersion is splitting white light into a rainbow, while scattering is light bouncing off particles in the air. Third, drawing these beautiful perfect ray diagrams, but totally forgetting to draw the little directional arrows on the lines. Guys, without arrows, it's just geometry, it's not physics. And finally, especially in your chemistry sections, forgetting your solid, liquid, or gas state symbols in your equations. Don't leave those out.
When it comes to physics numericals, you absolutely must follow this exact 4-step format to get full marks. Step 1, write down the given values. Step 2, Write out the exact formula you are using. Step 3, show the substitution of your numbers into that formula. And Step 4, write your final answer. And listen to me on this one, you absolutely must include the unit. If you just write R equals 10 instead of R equals 10 ohms, you will lose a mark, even if your math is completely flawless. Stepwise marking means every single line is an opportunity to score, so don't throw them away. We have covered a lot of ground today, zooming all the way from the tiny ciliary muscles inside your eyes right up to the scattering of light at the edge of space. So I'll leave you with this final thought. How does understanding the physics of light change the way you look at a simple sunset, a starry night, or even just your own eyes in the mirror? The world isn't just happening around you. It's this constant, measurable, and deeply fascinating interplay of biology and physics. Thank you so much for exploring this explainer with me today. Keep your curiosity sharp, keep studying smart, and I'll catch you next time.